This is session 13 for Models in Epidemiology and Biostatistics. I'm Gordon Hilton Fick. Well, for this session, and indeed for the sessions 13, 14, and 15, we're going to be looking at linear regression. In a way, if we were to follow things in a perhaps more historical way, we would have taken a look at linear regression earlier, or maybe even first. Some people, when they're presenting this material, do so. In any case, I've made the decision to include this material now. It is certainly true that these methods are very widely used, perhaps not quite to the same extent as they were a generation ago. Never mind. The methods that are going to be illustrated in these coming sessions really date back to the pioneering work of Ronald Fisher and William Gossett and others. In particular, William Gossett, publishing under the pseudonym Student, was the first to present a distribution that we now call the t-statistic, a distribution for the t-statistic. And then that pioneering work from 1908, published in Biometrica, it changed the way in which continuous outcomes have been analyzed forever, I guess. Maybe it's a little bit more dramatic than it should be. In any case, it was in 1925 that Ronald Fisher published work in which he showed that the early work of Gossett's deriving this t-distribution became the most widely used, certainly for many, many years, because he showed the wide applicability of the t-distribution to not just the very simplest of settings, but to the most elaborate, at least elaborate at the time, in so-called linear regression. It was at around that time when Professor Fisher also established what we now refer to as the analysis of variance. And that led to yet another probability distribution that Professor Fisher introduced at the time, and the form in which it's used now, the so-called F distribution, name for Fisher, F for Fisher, based on the ratio of estimates of variance. Well, I'm kind of jumping ahead a fair bit, but I thought I would just give you a little bit of the background, a little bit of the history here. There's an enormous amount that's been written about the history of what we would now call modern statistical inference. And indeed, there's the very fine book, the biography of Ronald Fisher by Joan Fisher Box, highly recommended. And a long list of fascinating literature and historical artifacts, I guess, connected with all of this material. The collection of Professor Fisher's writings spans 5 very long books. And you could spend your entire career attempting to understand only just a fraction of them. All right. So now let's get back on track here and talk about the purpose of today's session, and that is understanding how it is that we can go about the study of a measured outcome now. So far, we've been looking at dichotomous outcomes. We've looked at outcomes which have just a small number of levels. And we've looked at outcomes that can be described in terms of counts. But now what we're going to be doing is recognizing that there are a wide range of outcomes for which there's just too many possible values. Further, we have the notion of continuity, and that is that, at least in principle, all values within a particular range are at least possible. Now, there's lots of examples of this that are available. The point being is that, well, in reality, we measure these characteristics with finite accuracy, and that inevitably we really have a finite set of possibilities in practice. However, it becomes vastly more effective to simply acknowledge that the number of possible intervals and the study of all such intervals is out of the question. And indeed, it becomes vastly more relevant to simply assume that the outcome is essentially continuous. Now, before we do so, we might well have a quantity that we do measure, and then we are contemplating how to go about analysis. Well, one of the approaches still widely used and effectively used in some context is to take that measured outcome and to construct groups. The simplest being simply a classification. Maybe one measures a person's systolic blood pressure, but really the issue is the study of those who are hypertensive and those who are normotensive. And so inevitably that then suggests that we should try to study, perhaps, say, those individuals where the blood pressure is above, say, 130 millimeters of mercury, rather than actually studying the distribution of systolic blood pressure. Now, the first point that is often made here is that the establishment of these thresholds might then lead to an artifact in the analysis. In other words, we don't want our analysis to be dependent on the selection of the threshold. Now, in some literature, such thresholds have become very well established, and so the decision about that threshold might well be a done deal, perhaps. But on the other hand, we might argue that one threshold is not enough. There is a characteristic called the albumin excretion rate, or AER, widely studied in diabetes research, that has a distribution that is complicated in ways that I'll be discussing in a minute, but for which many people in the literature feel that 2 or possibly 4 thresholds are being considered here. So, for example, with two thresholds, we might say, well, a person with an albumin excretion rate below 20 would be considered normal. A person with an albumin excretion rate between 20 and 200 is sometimes called microalbuminuria, and albumin excretion rates over 200 considered macroalbuminuria, the most serious version of this. However, there are authors that would argue that microalbuminuria group ought to be split up, and so there's some discussion there. Is that enough? Is that enough intervals? So, but in any case, if we did have a set of intervals like that, then you could say, okay, at least they're ordinal now, rather than measured, okay? And it might well be that we get sometimes what might be called clinically relevant analyses rather than simply the study of the actual albumin excretion rate by some means. Okay, so the challenge of adopting these thresholds is one that's complicated. Now, there are some authors that write that one should never use such thresholds. There are arguments made, in my view, imperfectly, that analyses will always be inferior by using groupings like this. That is, in my view, a very limited discussion and doesn't really get at the heart of the matter here. So nevertheless, should we be using the actual values or should we be using thresholds and then intervals? These are not elementary topics, and ones that in your own field of health research, you may well come into contact with such thresholds or some arguments that you shouldn't use them. And this is maybe not the place for the resolution of any of that. Nevertheless, I guess it's fair to say that there are circumstances in which, even though you have a measured outcome, the primary outcome then, the outcome for primary analysis could be something other than the actual measurements themselves. Okay. So we're now going to come to then the study of the distribution of an outcome. And we've done that with the multinomial, which we saw a little while back. We've done that with the Poisson and the negative binomial. But now we're going to come to an investigation of distributions for which we have made the implicit assumption that the outcome is measured, that it is continuous. And further, we then will do for a good portion of this session, suppose that it makes sense to study the mean of that probability distribution, and that the mean does indeed reflect the center of the distribution in some sense, and that if in fact the distribution is symmetrical, then we have the fact that the study of the mean would be the same as the study of the median. And similarly, if the distribution is symmetrical and unimodal, then the discussion of the mean is like studying the mode of that distribution. So notice what I'm elaborating right now is the discussion of a single characteristic of that probability distribution that's judged to be the most important. And for the time being, we're going to suppose that that characteristic's the mean. But there are many people who would argue that we really do need the symmetry of the distribution, at least approximate symmetry of that distribution, in order that the mean becomes the quantity we want to study. I would say that it is incorrect to simply assume that the mean is what we wish to study. I think that if the distribution is, for example, skewed in some very definite quantifiable way, then it can be argued that the mean might well not be the characteristic that's of most interest. It could be that percentiles become more relevant, like the median, and so on. More on this later on. So I'm deliberately giving you a little more of the, if I may, the background here. I am anticipating that those of you who are watching this particular session have had some experience with the statistical inference that's used with the, if I may, classic analysis of measured outcomes. That being the inference based on the t-distribution, giving us a test of significance, the so-called t-test, or confidence limits, for the mean that come also from the t-distribution, and that you have probably seen, if maybe just briefly, some discussion of the distribution of the this ratio of variances that we'll discuss later, the so-called analysis of variance distribution, or F distribution. So then we're going to be studying the mean of a distribution that is conditional or specified by a collection of possible exposures, potential confounders or modifiers, and perhaps other explanatory variables that are deemed important to include in such an analysis. So now it's going to be an exploration of the mean exposure relationships. So the mean of that distribution, insofar as it's dependent on or conditional on an exposure or exposures, and whether or not that relationship between the mean and the exposures involves modification and or confounding. It's worth pointing out that that sometimes case control studies involve the direct study of an absolutely continuous exposure, as we might see in cancer studies, for example. And if, in fact, that's the case, then we now have a measured variable that becomes the quantity we wish to study. So then it becomes studying, for example, the expected exposure as a function of the case control status, and then possibly other confounder modifiers and so on. All right. So the study of linear regression. Well, it's a big topic. And as I said, I am not going to take too much time with the very elementary illustrations. I am anticipating that you find viewers of this session have had some experience with some of this material. Nevertheless, so one of the most fundamental issues for the investigation of a measured outcome is the symmetry issue that I've alluded to, and how we go about assessing such a symmetry, and then what are the implications if in fact the distribution is not symmetrical. Big topics, lots of options here. Nevertheless, let's now set the symmetry assessment aside and get to the classic material now, as it is established in most of the monographs and textbooks and presentations of this material. So now we're going to be looking at, again, the left-hand side of the equation will be a mean, and the right-hand side of the equation will be the linear combinations of the explanatory variables. Okay? So here we have then that the linear regression is the expected value conditional on explanatory variables being expressed as a linear combination. So the right-hand side of linear regression is the same as we've seen before. However, now our discussion is going to be in terms of expected values. Now you might note, and indeed correctly so, that some authors would say it's better to write this expectation as a conditional expectation. Just as you could argue that we should have done the same thing with, say, conditional log odds and other methods we will could be considering. Well, then the notation starts getting kind of complex, and I think it's worth pointing out that the means we're discussing here are always specialized to specific combinations of individuals, specific sets of possible explanatory variables. There are always going to be these conditions, okay? If there aren't, then we're really in a very elementary setting, I guess, aren't we? So keep in mind that nothing is really new here except that now the right-hand side is the linear combination of the explanatory variables, and the left-hand side is now an expected value, a mean. We will use expected value, an expectation, and mean interchangeably here, okay? So now we will see that our discussion of the regression coefficients will be in terms of expected values or means. And then, once we've conducted the analysis and collected the data and then analyzed the data and determined estimates of those regression coefficients, we can then see that we have estimates then of quantities expressed in terms of means. Okay, so then, fairly briefly then, let's take a look at the simplest settings as we've seen from the very beginning of these sessions. And that is, let's suppose we have simply two groups. We have a group of people receiving a standard form of a drug, and we have a group of people receiving a test form of the drug. And for illustration here, we might suppose that our outcome is actually a change score. It is the change in systolic blood pressure. So we are immediately going to another topic which we will be addressing in a much later session, and that is, should we be taking as our primary outcome change, or should we be using the actual values here? Another topic. I have a hard time focusing here, I guess. Sorry about that. In any case, we'll suppose that our outcome Y now is the change in systolic blood pressure. Okay. And then we could, and you would point out to me, I remember this. This is the two sample problem or two groups problem. And you might also be thinking, I know this. This would be something where the t-distribution would be used for a test and a confidence interval for the difference between the two means. The mean blood pressure for those receiving the test drug minus the mean blood pressure, change in blood pressure for those receiving the standard drug. Okay. And indeed, that is what is a part of most introductory courses. Right? All right, well, let's revisit this classic material in terms of our models. If we write the expected value of change in blood pressure here is beta naught plus beta 1x, where x is the indicator for the test drug here. Right? So we've coded 1 for test and 0 for standard. Then we can immediately see, like we did earlier in these sessions for logistic regression, that when x is 0, we see the expected value is beta sub 0. And for x equals 1, the expected value is beta sub 0 plus beta sub 1. Right. That's simply taking this equation and writing it with x equals 0, in which case this term goes away, and writing it when x is equal to 1, in which case we get the sum of the two. And so what can we see? If we take the difference between this equation and this equation for those receiving the test drug, and this equation for those receiving the standard drug, we get beta 1, beta sub 1. So we see then that beta sub 1 is in fact the expected change in blood pressure for those receiving the test drug minus the expected change in blood pressure for those receiving the standard drug. Okay, so we can see that right away, beta 1 is the quantity we would want to study. It's giving us the characteristic we are interested in. That is the difference between the two means. And you may be used to writing, say, mu sub 1 minus mu sub 0. Again, in your introduction to this classic material. Okay? So what have we done? We've taken our simple two sample problem or two groups problem and written it in terms of a simple linear regression. Let's take another example very briefly. Let's suppose that we have of interest that gender might be a potential confounder or modifier. And we know, like we saw then with our previous work, going back to the very first sessions on models, that this would be the model we would start with, where we would have the indicator for the test drug, the indicator for the males in the study here, and then the product of the two. Okay. Then we spent quite a bit of time with this right-hand side, where the left-hand side was the log of the odds. Now it's an expected value. So, for example, we can see right away what beta 1 is here. It is, for the females, the expected change in blood pressure for those receiving the test drug minus the expected change in blood pressure for those receiving the standard drug. How about that? It's just like before, right? How about beta 1 plus beta 3 here? Beta 1 plus beta 3 is, for the males, that same difference between means. And hence, beta 3, that difference between beta 1 plus beta 3 and beta 1, is measuring the extent to which the expected difference depends on gender. Very much like we've seen before. In other words, beta 3 is enabling us to assess whether gender modifies, in this case, the expected change in blood pressure relationship with the two drugs. Okay. And as I'm saying here, we've done this, right? The only thing that's new is the left-hand side. And everything we have learned about models regarding the right-hand side in the interpretation of the regression coefficients, everything carries forward. Instead, now in our descriptions, instead of describing things in terms of the log of odds as we did with logistic regression, it is now the expected value. Okay. Just like we did with the previous models, we then have the model and the fit. The literature is very mixed here. You'll see wide-ranging notation that's used here. You'll see some authors that instead of using the capital letter Y here, will use the lowercase y with a hat over it. Similarly here, the regression coefficient estimates here, the B's are sometimes seen with the betas with hats over them. Both are widely seen. They're identical. And like we saw in previous sessions, we can assess the quality of this fit by computing the difference between the observed and the fitted. That is the residual. Or, in this case, we'll use the letter E here, okay? For, as we'll see in a minute, the estimate of the error, okay? Now, it turns out that if In the classic scenario of, as we'll see in a minute, the assumption of constant variance, then the so-called least squares solution, very classic stuff, can be implemented. The least squares solution to the construction of the estimates of these regression coefficients can be done. Now you might be thinking, what happened to maximum likelihood? Well, it turns out that in this scenario, as we'll see in a little bit, with some additional assumptions, the assumption of constant variance, independence, and another issue I'm going to come to, the distributional assumption, we get that the least squares solution is the maximum likelihood solution. So the maximum likelihood here extends to the least squares solution. All right, a little bit of technical stuff here. And as I say, this literature is huge, and it's very old and very, very well established. So as I have alluded to, if we're comfortable with assuming a model like this for this measured outcome, and if we're comfortable with the study of the mean of these distributions, then we get fitted values based on the estimation of the regression coefficients. Okay, so what about these distributions that I've been alluding to here? You're thinking, I already know the answer to this, Gordon. This isn't a big surprise. The classic assumption that's made for the construction of the inference that follows from what I have illustrated so far is to assume that these distributions are the normal distribution. All right. But what's really in place here? Well, we've got the assumption of independence. The observations are not related, right? That's a big issue, and we'll be addressing that in sessions in the 20s and in the future. And we are interested in studying the mean of the distribution, right? And that it is a linear function, a linear combination of explanatory variables. And further, we're going to suppose that the variance, although unknown, is constant and not dependent on the explanatory variables. So we've got symmetry, independence, and constant variance. Okay. Now, it's worth noting here that with logistic regression, with the binomial model that we began with logistic regression, we didn't have to make an assumption about the variances. In fact, we cannot. It turns out that with logistic regression and variations on it, assuming the binomial distribution, the variances are not constant. That's not an issue. Further, the distributions aren't symmetrical either. They're binomial. They're Bernoulli. They're two spikes, right? They're not symmetrical, except in very specialized circumstances. Okay, now, more details. We have that if in fact we're prepared to assume that the conditional distributions are not only symmetrical, but are of the very specific form, that is, the classic normal distribution, then the p-values and confidence intervals we get based on the t-distribution and that are based on the t-distribution are exact in the sense that there is no approximation required. The exactness issue was one that we have skirted for the most part with regard to logistic regression. Most of the methods we've illustrated to date involve approximations or asymptotics, right? Nevertheless, if in fact the distributions are assumed to be normal, then the p-values and confidence intervals based on the t-distribution are exact. On the other hand, if the distributions are only thought to be symmetrical but not precisely normally distributed, then the p-values and confidence intervals are approximate as before. We'll also see, as we proceed through this investigation, that we have another kind of test for comparing several regression coefficients at once. And that, as we'll see in a little bit, it leads us to the classic F distributions. Okay. Further, there's a relationship between, as it turns out, two-sided t-tests and one-sided f-tests. And again, that relationship isn't approximate anymore. It's actually exact. Again, if one is prepared to assume normality for the distributions for the errors. Okay, well, what about these errors then? What about the errors? All right. Well, the errors typically are written with the symbol Z here, the classic notation for the standard normal distribution here, the Zs. And what I've done is rewritten the model in terms of the actual value, the regression coefficients, and the errors. This way of writing the model in linear regression has a lot of advantage. And we will see that it appears in linear regression and in a small set of other types where it is effective to display the outcome itself rather than the quantity being studied about that outcome. Okay? Nevertheless, we really are seeing that this is the right-hand side of the equation expressed in terms of the expectation plus this independent standard normal Z, error Z, scaled by the constant standard deviation sigma. So this is, again, we're talking about the distribution being normal, the variances being constant, the explanatory variables impacting on the outcome by linear combinations of those characteristics, and that giving us the estimates. All right. Now, one other way in which one often sees these models written is this way. In other words, where the Greek letter epsilon is included here to encompass both the Z and the sigma here. So the errors here are these quantities, epsilons, and the estimates of the errors are the residuals, the E's. So here I'm coming full circle for you here. So in the model, we can have the errors represented by epsilons, and in the fit, we can then have the actual, the fit, and the residual expressed as a single equation as well. Here, the E's estimate the epsilons. Okay? Okay. So there's a fair bit of overhead to getting used to linear regression and various different presentations. And I'm trying to give them to you all at once here. Another widely seen way of describing the fitted values and their relationship to the observed values is this equation in which we standardize the residual by some means. The usual way to scale them so that they have constant variance of 1. So getting your head around all of this notation and the massive history associated with all of this material can be a bit demoralizing maybe. One thing that I will add to the mix then is that we have that this quantity S here that's used to standardize the residuals is typically viewed as the quantity we wish to use to estimate the unknown error standard deviation. The residuals either standardized here or raw, without the standardization, are then obtained after we've constructed the fit. Now, keep in mind then that the errors in this presentation we're looking at here are assumed to be independent. However, the residuals, these E's or the R's, are not independent, and that comes from the fact that the residuals are products of this whole estimation process. So keep in mind then that the errors are assumed to be independent, but the residuals are not typically independent. Sometimes close to being so, but that's not the issue. All right, so a fair bit of stuff, right? And a little more then. How about we look now at the next big issue that is classic here, and that is the analysis of variance. So really early, back to the 1920s again, my goodness, now we are in that range of years where all of this material is essentially celebrating its 100th anniversary. The 100th anniversary of the development of these methods. Wow. So it turned out that way back in the 1920s, Professor Fisher established a means for testing hypotheses for comparing two or more means by means of a process that involved a comparison of estimates of the assumed common variance. And those original papers are worth looking at. In those original works, he constructed a test based on the difference between the logarithms of the two estimates of variance, rather than the ratio of the estimates of variance directly. So Professor Fisher felt that it was better to analyze things on the logarithmic scale back then. How about that, eh? However, it is evolved over time that the quantity that is most often reported in this setting is the ratio of the estimates of variance directly, without taking the logarithm. And it was quite some time ago that particular probability distribution came into common use, and these are the F distributions now, and the F is indeed for Professor Fisher. The decision to present the results in terms of the actual ratio of estimates rather than the difference between the logarithms may have been attributed to the American statistician George Snedeker. I can't be absolutely sure that he was the first to do so here. Maybe historians will figure this out. So the analysis of variance here really enabled researchers to understand much more complicated mechanisms than were previously available. The challenge in those early years was that the calculations, which were all done by hand back in those early days, could be done only in comparatively rarefied situations. The experiments were and are now described as being orthogonal, or the word orthogonality and balance are often seen. Well, it turns out that the use of the analysis of variance in its clearest form, its simplest form, means that one needs to have exactly the same number of subjects in each of the groups. So if you've got, say, 3 groups, then you need to have exactly the same number of participants in each group. Well, especially in health research, that type of balance or orthogonality here is rarely seen. There's going to be circumstances with the assignment of individuals to treatments, even in carefully controlled clinical trials where there's going to be people who withdraw or they're lost to follow-up. In any case, the loss of orthogonality here in the use of the analysis of variance became a very big deal. And in part, this led to a challenge to the understanding of many of the methods that Fisher described with the analysis of variance. Now, if one has the good fortune to have balance, one gets a certain clarity of understanding, and certain things become a lot more straightforward than they are in, shall we say, the real world, where, well, nope, we don't have orthogonality. We do not have this nice balance. And in fact, to stay within the methods of the analysis of variance leads to very complicated analysis strategies. And there was a time before the advent of modern, shall we say, modern computing with the classic software we use now, like Stata and R and others, where authors looked for ways to carry out analyses without the circumstance of orthogonality, and then, well, a lot more additional work. Most of that material, not all, but most of that material, although interesting historically, is not relevant anymore. But you'll still see it introduced in some places, and indeed, there is merit to appreciating the implications. Very early work on the analysis of missing values does provide us with some insight into the complex issue of lack of balance or loss of orthogonality. Okay. So it turns out that if we have equal numbers, that we can still get some pretty elaborate looking analyses, and we can do so essentially by hand. Most of the key steps in the analysis can be done as we're going to see in a minute here. I have an example for you of a classic randomized clinical trial where there were equal numbers of individuals in each of the groups, and there was no losses. There were no loss to follow-ups, and there were no withdrawals. And I think there is some merit to going through this particular exercise, and that's what we're going to do next. So what we're going to do is use an example taken from the book A Handbook of Statistical Analyses Using Stata by Sophia Rabe-Hesketh and Brian Everett. There are several editions of this book available. I think the most current one is the 4th edition, but this illustration is in each of the editions, if I'm not mistaken, and the actual page number you may need to just do a little bit of scanning to make sure you've got the right reference and the right example. In any case, I'm providing you with this data in Stata format, and there are circumstances I'd like to now give to you. Turns out that the study itself was conducted and published by Maxwell and Delaney in 1990. And they're wondering about the study of 3 treatments for hypertension. And we'll use the anonymized version, as was done in Rabe-Hesketh and Everett, and simply refer to the medications as drug X, drug Y, and drug Z. And we'll code them 1, 2, and 3. Further in this investigation, there was a physiological feedback variable, a so-called biofeedback variable, that was present or absent, and then there was the use of a diet that might help. So we've got drug, diet, and biofeedback. Drug with 3 levels, diet with 2 levels, and the special level, the special form of diet coded 1, and the biofeedback, yes, no, and the presence of biofeedback here, coded 1. And for this particular study, they had then 12 combinations, right? We've got 3 times 2 times 2. There are 12 different experimental settings here, 12 different groups. And it turned out that they were able to recruit 72 people and then make a random allocation of these 12 different regimes to sets of 6 individuals. So there were 6 individuals in each of the 12 different groups, and that gave us the total of 72. You could refer to the actual data here in bp.dta and use the data visualizer to actually see how this data would be configured in an analysis. Further, so here we could view all 3 of these variables as exposures. You could do that. Or, given that the drug issue was primary here, this exposure to one of the 3 drugs could be viewed as primary, and that diet and biofeedback might be viewed here as potential confounder modifiers. This brings up an issue that will come up quite often, and that is, how do you wish to present the project? My own thinking on this right now is that it may be best to have a primary explanatory variable here, the drug variable, view it as the exposure, and view diet and biofeedback as secondary variables, or ones that might be giving us issues of modification or confounding. Now I'm showing you what was given in Rabe, Hesketh, and Everett, and that is what is typically called the so-called preliminary analysis of variance table. The reason being here is that there are 12 groups and 11 degrees of freedom representing differences among the 12 groups, and that 11 degrees of freedom can be separated into these pieces. Now, since we have 3 drugs, that means there's 2 degrees of freedom reflecting differences among the 3, and further there are degrees of freedom associated with the drug diet perhaps interaction, and indeed this most complicated of settings in which we have sometimes it's called a 3-factor interaction here, right? Where we have diet, drug, biofeedback with 2 degrees of freedom. Now, this is sometimes called a preliminary analysis of variance table, in that we have not separated out all the individual pieces here. We have these sets of 2 rather than all of the 1 degree of freedom pieces, all detailed. Again, a fair bit of lingo here, isn't there? Yes. All right. So what we can see, though, straight off the bat, is that if we were to view, for example, the drug variable as the primary one, and that the diet and biofeedback are potential confounder modifiers, what do we see straight away from this preliminary analysis? We get, from this approach, a 2 degree of freedom test with an F statistic of 3.43 and a p-value that's less than 5% here. And what are we getting? We're getting an indication here, an omnibus one, but an indication that the comparison between the drugs depends on the diet biofeedback combination that the participants receive. So what we're seeing then is that the relationship between expected blood pressure and drug is modified in some way by diet and biofeedback. Now, this would be somewhat analogous, I guess, to our stratified analyses where we have multiple degrees of freedom here, and we don't necessarily get a clear message as to the nature of this expected blood pressure drug relationship insofar as it's modified by diet and biofeedback. Okay? So we might then say, can I have more? And the answer, as I think you can anticipate, is very definitely yes. We can have much more. We can now look at specific comparisons. Now, I think you can also anticipate what we're going to be doing here. We're going to construct for the 3 different drug groups. We'll choose a baseline group and make our comparisons relative to that baseline group. And that's going to take us then to, instead of, in this instance, an analysis of variance, an approach that will be based on linear regression. Now, first of all, I should also mention that all of the analyses for this particular type of study can be done, and the separation into individual degrees of freedom can be done entirely within an analysis of variance. All right, let's proceed now and carry out a possible analysis using linear regression here now, and see what parts of this approach would be the same as we get from an analysis of variance and where there are differences. So we will then establish explanatory variables for the drug-coded 2, the drug-coded 3. In other words, Y and Z. Now you could say we could generate the variable X for drug equals 1, but drug equals 1 or drug X will be baseline here. Then we can construct the other products just like we have done with logistic regression. Okay? And here are the codings and the labels for the codes, and then the various combinations of these variables. Notice now we are splitting up that 2 degrees of freedom associated with this interesting identification we saw of there being modification based on diet and biofeedback. Where we're splitting it up into 2 by having a comparison between drug Y and drug X and a comparison between drug Z and drug X. And that gives us everything else. Okay, let's take a look at some results here. And here is where I strongly recommend you spend some time disassembling this analysis. This is where you're really going to get a strong grounding as to the issues here. This illustration I've taken from Ray Hesketh and Everett may seem a little elaborate, but in a minute you're going to see that in fact it is in fact pretty straightforward in so many ways. Now, the first thing that we need to identify and remember is that we do have orthogonality here. We do have this balance issue. We have exactly 6 participants in each of the 12 groups. And what do we see? If we use the table command in Stata and ask for the average blood pressure measurement in each of the 12 groups, we see, for example, that the 6 participants in the group that received drug X, that received the normal diet and had no biofeedback, had an average of 188. So keep in mind, this is, if I may, our baseline group. We've chosen drug X as baseline for the so all our comparisons will be between the other drugs Y and Z, and drug X, and this normal no biofeedback corresponds to baseline as well. That is that we have the code of 0 for the normal diet and 0 for the absence of biofeedback. All right. So now let's take a look at, here's the results, but here's the model that I've written down here, looking pretty intimidating. On the other hand, these regression coefficients are all just simply differences among averages. Okay? And all of these pieces can be interpreted, just like we did with logistic regression. All of these estimates of the regression coefficients can be interpreted. All of the regression coefficients, all 12 of them here, can be interpreted. It's not going to be, as we'll see in a minute, that terribly difficult. All right, let's take an example. Let's take the example of beta naught here. Beta naught is indeed the expected blood pressure for those receiving drug X, for those receiving the normal diet, and for those receiving no biofeedback. So that is an expected value, beta naught. Again, you can specialize all of these pieces. You may find it instructive to do so. All right, now let's dig into the estimates of the regression coefficients here. Here they are. Aha! Underscore CONS for constant here is then our estimate of beta naught, or B sub 0. And you can see here, we get 188. What's that number? That number is indeed the estimate of beta naught. And it is indeed the average of the 6 measurements taken from those 6 participants that received drug X, that received the normal diet and did not receive biofeedback. And there it is right there, the actual average. So you'll recall we did this sort of thing in the logistic regression too. How to take the actual data here and see it in the context of a regression analysis. Not too bad. Let's take another couple of examples here to help you to appreciate how to demystify these numbers, okay? To help you to appreciate the issues in play here. All right. Let's look at beta 1, for example. Beta 1 here. Beta 1 is then the difference between 2 means. It's the difference between the mean for those receiving drug Y, normal diet, and no biofeedback, minus the mean for those receiving drug Y, normal diet, it's drug X minus drug Y, specifically for those receiving the normal diet and no biofeedback. Okay, so beta 1, I muddled that a bit. Let me try it again. It is indeed a difference between the 2 expected values. The expected value for those receiving drug Y, normal diet, and no biofeedback, minus those receiving drug X, no special diet, no biofeedback. That's beta 1. It is a difference between two means. What is that in this particular instance? It is we can now look at the estimate of beta 1, which is our B1 here. And what is it? It's 12. So that is an estimate of the difference between the expectation for those receiving drug Y, normal diet, and no biofeedback, minus the expectation when those receiving drug X, no normal diet, and no biofeedback. In other words, it is a difference between two averages. It is the difference between 200 here. Here it is. I'm using the pointer again here. 200 and 188. 200 minus 188 is 12. In other words, that number 12 is not so mysterious. It is, in fact, merely a difference between two averages. Now, we have this simple observation here, these simple differences, these simple means to determine the estimates because of the balance, because of the fact that we've got the same number of participants in every group. So we're getting a simple version of things, right? The real world where we don't have the same numbers in every group won't give us the ability to determine precisely what the estimates are, but we can determine what it is we are estimating in terms of the population characteristics. Every one of these estimates of regression coefficients can be computed simply by hand as differences and as differences between differences. And then lastly, when we're looking at these more complicated ones at the very end, then we're looking at differences between one of the drugs and drug X, and then also thinking about the differences relative to the diet and the biofeedback. So differences between differences, and then differences between differences. Yeah, maybe getting a little bit wild, but not, again, take some time. If you're feeling intimidated by this, take some time and see if you can't resolve all of these regression coefficients in terms of the averages in the 12 groups. Keeping in mind that our ability to do so is based on the fact that we have exact balance, that we have this form of orthogonality here. And I'm also showing you here that we could have, from this regression analysis, made precisely the same test of significance we did from the analysis of variance. That is, the 2 degrees of freedom test based on YSB and ZSB. Simultaneously testing these two gives us the F statistic with 2 degrees of freedom and 60 degrees of freedom, and exactly the same p-value we got from the analysis of variance, the so-called preliminary analysis of variance. However, in this analysis, we can see that indeed it appears that it is the comparison between drug Y and drug X that is modified by the diet and the biofeedback. Right? This comparison of the two appears to be the one in play. Now notice, if this was the planned analysis here, we would have seen this, maybe you could say more precisely here, the actual nature of this modification involving the special diet and biofeedback being associated with the comparison between drug Y and drug X. and not apparently comparing drug Z with drug X. And there's many other comparisons we could make here. Once we've done this regression analysis, one can construct various F-tests or T-tests as we wish in a particular circumstance. And it's very nicely laid out in all the software that we might use here. And I'm illustrating it here for Stata, but indeed, all of the quality software systems like R, for example, and others do this kind of thing for you. So, for your interest, I have shown you how we can compute some of them, and and so that you can gain a grounding. Keep in mind that each of the regression coefficients involves a population characteristic, and then the estimates we get that are available by simple calculation in this instance because of the balance. And I recommend you spend some time with this. And as I've noted, and as many people will observe, in the description of these regression coefficients and or their estimates get us into quite long sentences. Yes. To simply state what's going on. However, while it's long and detailed, it isn't hard. It is merely complex, I guess, would be the better way to describe it. On the other hand, it means that every part of this separation of these regression coefficients can be demystified. The computation of the standard errors and the other pieces all come from the classic theory that was done all those years ago in 1925 in its earliest days by Professor Fisher, and is very standard material, where the formulas, again, you can find in lots of quality places. The formulas for these things you can look up. Our goal here, though, is more about the interpretation and using the quality software to enable us to complete these calculations. Now, there's one other issue that is worth pointing out here that requires some attention. And I alluded to this with some of my early remarks, and that is the components of an analysis of variance and a regression analysis are intended to give us the same pieces here. However, one has to be cautious when one looks at the pieces of the analysis of variance and compares them with the pieces in the regression analysis. They aren't always the same. One needs to be cautious here. How do you stay out of trouble? By interpreting the various quantities, either in the regression analysis here or in the analysis of variance. So I'll point out to you here that the pieces of the regression analysis involve I'll go back to the display here, quite specific comparisons. As we've seen, the interpretation of these coefficients requires considerable care, in that they are said to be so-called simple or specific to the particular agenda here. These are specific comparisons. Again, you see that by interpreting these regression coefficients from this model. Okay? Now, from the analysis of variance, though, we have notions that are classic, but are now subject to oftentimes misinterpretation. In the language of the analysis of variance, we sometimes see, and indeed we very often see, the so-called main effect description. Now, in the world of regression analysis with the indicator variables approach that I've established here, there is no direct computation of the so-called main effect. Now, notice from the analysis of variance table that we get an f-test of diet here, which is 33.20. Now, that is very directly a comparison between the 36 people receiving special diet and the 36 people receiving the normal diet. The t-test, or the corresponding f-test, is simply comparing these 36, the average made up of these 36 measurements with these 36 measurements. Okay? Now, that might seem like a perfectly sensible thing to do, perhaps. But notice this is not the same as the corresponding t-test. And we'll look at this in a minute. So this is comparing two averages, each based on 36. Okay? And one can see that, in fact, this so-called main effect, and I'm putting this in quotes here, is comparing the diets ignoring the drug and biofeedback characteristics, pretending that there was no issue here. Now, what about the t-test that's a part of this regression analysis? Well, the first thing we'll notice is that the t-statistic that we get is minus 2.08 and not this number 5.762. Okay? Let me just take you back to those two places in the two analyses we've seen. First, from the analysis of variance, we got diet here, and this F statistic and this very low p-value. That is a so-called main effect comparison, or a main comparison. This is diet ignoring drug and ignoring biofeedback. Okay? On the other hand, the regression analysis is quite different. The corresponding, or apparently corresponding, quantity here is the coefficient corresponding to, in this instance, beta 3. This is the estimate of beta 3, which is B3, which is minus 15. What is minus 15? Well, now let's walk through this. It is, in fact, comparing those receiving the special diet and those receiving the normal diet, but it's specialized to those in the group receiving drug X and receiving no biofeedback. Okay? Let's have a look. Let's see if we can't interpret this. It's the comparison between those receiving the special diet, that's this group, minus those receiving the normal diet, and those receiving drug X, and no biofeedback. Notice here, that is 173 minus 188. That is minus 15. So notice the regression coefficient is said to be specific. It is a comparison between special diet and normal diet, but specific to the baseline level of the other two, drug X and no biofeedback. Okay? So this regression coefficient, minus 15, is not the same as the main effect comparison we get from the analysis of variance, where we are comparing the normal diet and the special diet, ignoring the drug and ignoring the biofeedback level. So notice I'll stay on this for a bit. The minus 15 here is a difference between two numbers. Here, a difference between this average based on 6 individuals and this number based on 6 individuals. Whereas the so-called main effect from the analysis of variance is something very different. It is comparing the 36 individuals in total receiving special diet with the 36 individuals receiving the normal diet. Now this, I'm emphasizing this, I guess, for an important reason, and that is that it is often when people interpret the results of a regression analysis, they will incorrectly use the language of main effects or main comparisons. They are not. Typically, they are not when they are set up, as I have done so here, with indicator variables for all of the characteristics. Okay? So, going back then to this, it is worth then pointing out that what we get from the analysis of variance and what we get from the regression analysis may not be the same. You need to do the heavy lifting. You need to check what exactly is it that is being compared. And is it a so-called simple comparison? That is with, here in our example, special diet compared with normal diet, but specific to those receiving drug X and no biofeedback? Or is it a main comparison? In other words, comparing just the special diet people with the normal diet people, ignoring the other two characteristics. You need to be careful. And so that when you are writing up your results, you don't make that mistake that appears in so many settings. Okay? Now, there's a fair bit in play here. We could see, for example, that if we had proceeded with the analysis of variance approach with the omnibus test with 2 degrees of freedom, we might have proceeded with the process of removing that particular term or interpreting other components of that analysis of variance display. Now, whereas with the regression analysis approach, it might be somewhat different in that we might then say, well, I've got evidence of the fact that the comparison between drug Y and drug X depends on combinations of diet and biofeedback, but the comparison between drug Z and drug X apparently does not depend on the combinations of diet and biofeedback. Okay? And, well, one could then proceed with a different set of regression analyses, and where we would then part company with how we would have carried out this analysis if we had done so with the analysis of variance. Okay, so there's pieces here, isn't there? There's things that we need to be careful about, and it is again, if you are perhaps in your own work being asked to use the analysis of variance, especially if you have the luxury of exact balance or exact orthogonality, then that's fine. However, you need to be cautious about the interpretation of the components of that analysis of variance table, and the fact that the interpretations you make may not be the same as those that would have been made had I carried out the methodology based on regression analysis, which has the illusion of being exactly the same. Can be exactly the same, but again, that's going to take us miles away from where we want to go here. Not the issue here. And you might be also thinking, this is getting kind of complicated, and how are we going to interpret this? And blah, blah, blah. All right. One other point for you I'll make, and that is that you'll notice that I use complete phrases when describing most tools. Not all the time. I'm guilty of using abbreviations. I do, to this day, still prefer to refer to the analysis of variance, because that's what it is. It is comparing estimates of variance to address hypotheses about differences between means. It is, if I've got the history right, it was widely established by Professor John Tukey, a brilliant and amazing contributor to mathematics and statistics, that John Tukey, I believe, might have been the first to use. He used a lot of abbreviations, and one of them he used was ANOVA. And I personally, and I am a part of a group of many statisticians, biostatisticians, data analysts who don't like using the abbreviations. Why not use the actual words rather than all of the lingo, all of the abbreviations?